Tonight, we're going to look at what may be the strangest contradiction the James Webb Space Telescope has produced since it began operations. The galaxies that JWST is finding at the very edge of the observable universe are not, by every careful description, behaving the way they should. They appear too old. They appear too massive. They appear too mature. They appear, in specific quantitative ways, older than the universe that was supposed to have made them. The contradiction is, by every careful estimate, real. The galaxies exist. The measurements are reproducible. The implications are substantial. The standard cosmological framework, refined over the past century by generations of theoretical and observational work, predicts specific things about how galaxies should look in the very early universe. They should be small. They should be young. They should be barely assembled. They should be primarily composed of fresh hydrogen and helium gas, with only trace amounts of heavier elements. They should be irregular in shape, with star formation happening in scattered clumps rather than in organised structures. They should be, in essentially every measurable property, the precursors of the galaxies we observe at later cosmic epochs. But the galaxies JWST has found at the highest redshifts are, by every careful description, not behaving like precursors. They are behaving like mature galaxies that have already lived through billions of years of cosmic evolution. They have organized disk structures. They have populated stellar populations with substantial heavy element enrichment. They have masses far larger than the standard framework predicts. They have, in some cases, stellar populations that appear older than the cosmic age available for them to have formed. The framework predicts they should not exist. The observations show they do. By the end of tonight, you're going to understand the original cosmological predictions for the very early universe, the specific JWST observations that have contradicted those predictions. The most striking individual galaxies in the contradiction catalogue, including Jades GS, Z14-0, and Maisie's galaxy and several others. The detailed observational evidence for stellar populations older than the cosmic age, the proposed theoretical explanations including modified star formation physics and modified cosmology, the broader implications for our understanding of the early universe, and what the next generation of observations will reveal. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what the standard cosmological framework actually predicts about the very early universe. The framework is called Lambda Cold Dark Matter, or LCDM. The framework was developed over the second half of the 20th century through the combined work of many theoretical physicists and observational cosmologists. It is, by every careful description, one of the most successful theoretical frameworks in modern science. The framework has correctly predicted in considerable quantitative detail the cosmic microwave background, the large-scale structure of galaxy distributions, the abundances of the light chemical elements produced in Big Bang nucleosynthesis, and many other observational properties of the universe. The framework is, by every careful estimate, the foundation of essentially all current work in cosmology. The standard framework makes specific predictions for what the very early universe should look like. The first stars are predicted to form approximately 100 to 200 million years after the Big Bang. The first stars, called population 3 stars, in the standard terminology, are predicted to be very different from later stellar generations. They are predicted to be substantially more massive, with typical masses of a few tens to a few hundreds of solar masses. They are predicted to be primarily composed of hydrogen and helium, with essentially no heavier elements available in the early universe. They are predicted to live short lives, exhausting their nuclear fuel within a few million years, and dying as supernovae that scatter heavier elements into the surrounding gas. The first galaxies are predicted to form somewhat later, as the gas in cosmic dark matter halos, cools and collapses to form the next generations of stars. The first galaxies are predicted to appear approximately 200 to 400 million years after the Big Bang. The first galaxies are predicted to be small. The total stellar mass of a typical first galaxy is predicted to be approximately 1 million to 10 million solar masses. The first galaxies are predicted to be irregular. The dynamical conditions in the early universe, with gas inflows happening rapidly and chaotically, are not conducive to the formation of organized disk structures. The first galaxies are predicted to be metal-poor. The cumulative chemical enrichment from previous stellar generations is predicted to be small, with metallicities approximately 1/10 to 1/100th of the local universe values. The first galaxies are predicted to be actively forming stars. The available gas reservoirs are large, the cooling conditions favor rapid star formation, and the resulting populations should show evidence of substantial ongoing stellar nucleosynthesis. The detailed predictions for the observational properties of the first galaxies have been worked out by various theoretical groups. The teams led by Volker Brom at the University of Texas at Austin, Naoki Yoshida at the University of Tokyo, Aaron Smith at the Massachusetts Institute of Technology, and others have produced detailed simulations that follow the formation of the first galaxies from cosmic initial conditions to the production of observable stellar populations. The simulations are computationally intensive and have been continuously refined over the past 2 decades. The current state of the simulations is, by every careful description, advanced. They include detailed treatment of the gravitational dynamics, the gas hydrodynamics, the radiative transfer, the chemical evolution, and the feedback from supernovae and stellar winds. The detailed predictions from the simulations match, by every careful estimate, the observations of galaxies at moderate redshifts of approximately 1 to 3. The framework correctly reproduces in considerable quantitative detail the observed properties of galaxies at cosmic ages of approximately 2 to 5 billion years after the Big Bang. The framework predicts that as we look back to earlier cosmic epochs, we should see galaxies that are progressively smaller, younger, more metal-poor, and more irregular. The predictions are, by every careful description, specific and quantitatively detailed. The standard framework also predicts the cosmic timeline of galaxy assembly. The first dark matter halos form at very early cosmic epochs, with masses of approximately 1 million solar masses by 100 million years after the Big Bang. The halos grow through accretion and mergers over the subsequent cosmic history. The galaxies inside the halos grow through ongoing star formation, with stellar masses building up gradually over hundreds of millions of years. The detailed timeline predicts specific stellar masses, ages, and metallicities at each cosmic epoch. The predictions are, by every careful estimate, testable through direct observation, but the JWST observations have, by every careful description, contradicted the standard predictions in specific and substantial ways. The galaxies at the highest redshifts are not behaving like the framework predicts. The contradictions are not subtle. They are, by every careful estimate, factors of several to 100 in the relevant quantitative measures. The framework requires modification. The next sections of our conversation tonight will work through the specific JWST observations that have created the contradictions and the proposed modifications to the standard framework that may be required to accommodate them. Let's now look at how the James Webb Space Telescope is able to observe the very earliest galaxies and what specific observational capabilities have made the new measurements possible. The capabilities are, by every careful description, substantially beyond what any previous telescope has achieved. The advances are not incremental. They are, by every careful estimate, transformational for the study of the early universe. The James Webb Space Telescope was launched on December 25, 2021, after more than 2 decades of development. The telescope was a joint mission of the National Aeronautics and Space Administration, the European Space Agency, and the Canadian Space Agency. The development was led, on the NASA side, by John Mather at the NASA Goddard Space Flight Center. The mission has cost approximately $10 billion over its development and operations. The telescope reached its operational position at the Sun-Earth Lagrange point L2 in January 2022 and began science operations in July 2022. The telescope has, by every careful description, performed essentially flawlessly since its commissioning. The performance has, in several specific metrics, exceeded the pre-launch expectations. The technical specifications of the telescope are, by every careful estimate, what enable the observations of the earliest galaxies. The telescope has a 6.5-meter primary mirror, more than twice the diameter of the Hubble Space Telescope's mirror. The larger mirror collects approximately 7 times more light than Hubble. The telescope is optimized for infrared observations with sensitivity in wavelengths from approximately 0.6 microns to 28 microns. The infrared sensitivity is essential for observations of the early universe. The light from very distant galaxies is, by every careful description, redshifted by the expansion of the universe. The cumulative redshift moves the visible light emitted by these galaxies into the infrared range, where Hubble could not see it, but JWST can. The detailed observational capabilities of JWST include the near-infrared camera, the near-infrared spectrograph, the mid-infrared instrument, and the fine guidance sensor, with the near-infrared imager and slitless spectrograph. Each instrument provides different capabilities that are useful for studying the earliest galaxies. The near-infrared camera provides high-resolution imaging at near-infrared wavelengths, allowing the detection and morphological characterization of distant galaxies. The near-infrared spectrograph provides moderate-resolution spectroscopy at near-infrared wavelengths, allowing the measurement of redshifts, chemical compositions, and stellar population properties. The mid-infrared instrument provides imaging and spectroscopy at longer wavelengths, allowing observations of cooler stellar populations and dust. The fine guidance sensor with the near-infrared imager and slitless spectrograph provides additional spectroscopic capabilities at specific wavelengths. The combined capabilities allow, by every careful estimate, the detailed characterization of galaxies at redshifts higher than any previous telescope could achieve. The detailed observational programs for studying the earliest galaxies are organized into specific large-scale surveys. The JDS program, the JWST Advanced Deep Extragalactic Survey, is one of the largest. JDS is led by Daniel Eisenstein at the Center for Astrophysics, Harvard, and Smithsonian, and includes hundreds of scientists from institutions around the world. JWST uses the near-infrared camera and the near-infrared spectrograph to image and spectroscopically characterize a large field of view in the southern sky. The SEERS program, the Cosmic Evolution Early Release Science Survey, is another major program. SEERS is led by Stephen Finkelstein at the University of Texas at Austin. SEERS uses similar instruments but targets a different field in the northern sky. The UNCOVER program, the ultra-deep NIRSpec and NIRCam observations before the epoch of Ryanization, is led by Ivo Laber at Swinburne University. UNCOVER targets a different field again and uses different observational strategies. The combined catalogue of early galaxies from these programs is, by every careful description, far larger than any previous high redshift survey. The JWST surveys have, by every careful estimate, increased the number of confirmed galaxies at redshifts greater than 10 by approximately a factor of 100 compared to the pre-JWST era. The catalogue is, by every careful description, still growing rapidly. New observations are being added monthly. The detailed properties of the individual galaxies are being characterized through follow-up spectroscopy and modeling. The detailed analysis is, by every careful estimate, an active area of investigation that involves substantial fractions of the global cosmology research community. The detailed results of all this work are, by every careful description, what have created the contradictions with the standard framework that we will discuss in the next sections of our conversation tonight. The contradictions are, by every careful estimate, real and substantial. The framework requires modification. Let's now work through the specific galaxies that JWST has identified at the highest redshifts and what makes each of them remarkable. The individual galaxies are, by every careful description, where the contradictions with the standard framework become concrete. Each galaxy is a specific data point. The combined catalogue of these data points is, by every careful estimate, what has driven the broader theoretical reconsideration that is currently underway. Tonight, we will work through the most striking individual examples one by one. The first galaxy is JD's GS ZT-0. The galaxy was identified through JWST observations published in 2024. The discovery was led by Stefano Carniani at the Scuola Normale Superiore in Pisa, with collaborators from the broader JD's team. The galaxy is, by every careful estimate, the most distant galaxy currently confirmed through spectroscopic observations. The redshift is approximately 14.3, corresponding to a cosmic age of approximately 290 million years after the Big Bang. The galaxy has, by every careful description, properties that the standard framework cannot easily accommodate. The estimated stellar mass is approximately 100 million solar masses, far larger than the framework predicts for galaxies at this cosmic epoch. The galaxy shows evidence of substantial heavy element enrichment, with metallicities approximately 1/10 of the local universe values. The framework predicts essentially pristine gas compositions at this cosmic age. The galaxy appears compact, but resolved, with a physical size of approximately 1 kiloparsec. The morphology is, by every careful estimate, more organised than the framework predicts for galaxies at this cosmic epoch. The second galaxy is Maisie's galaxy. The galaxy was identified through JWST observations published in 2023. The discovery was led by Pablo Arrabal Haro and Stephen Finkelstein at the University of Texas at Austin, with collaborators from the SEERS team. The galaxy is at a redshift of approximately 11.4, corresponding to a cosmic age of approximately 400 million years after the Big Bang. The galaxy is named after Stephen Finkelstein's daughter. The galaxy has, by every careful description, an estimated stellar mass of approximately 100 million solar masses. The galaxy shows evidence of substantial star formation, with rates of approximately 10 solar masses per year. The galaxy appears, by every careful estimate, to be substantially more massive and more evolved than the standard framework predicts for galaxies at this cosmic epoch. The third galaxy is GHZ2, also known as GSZ11-0. The galaxy was identified through JWST observations published in 2023. The discovery was led by Marco Castellano at the Italian National Institute for Astrophysics. The galaxy is at a redshift of approximately 12.4, corresponding to a cosmic age of approximately 350 million years after the Big Bang. The galaxy has, by every careful description, properties that have generated substantial discussion in the cosmology community. The estimated stellar mass is approximately a few hundred million solar masses. The galaxy appears compact and bright, with significant ultraviolet luminosity. The detailed spectroscopic properties suggest, by every careful estimate, a substantially evolved stellar population. The galaxy is, by every careful description, one of the most striking examples of the contradictions with the standard framework. The fourth galaxy is GSZ31. The galaxy was identified through JWST observations and is at a redshift of approximately 13.1, corresponding to a cosmic age of approximately 320 million years after the Big Bang. The galaxy has, by every careful estimate, an estimated stellar mass of approximately 50 million solar masses. The detailed spectroscopic properties suggest substantial evolution, with chemical enrichment that the standard framework cannot easily produce in the available cosmic time. The fifth galaxy is JADES NS1. The galaxy was identified through detailed JADES spectroscopic observations. The galaxy is at a redshift of approximately 10.6, corresponding to a cosmic age of approximately 440 million years after the Big Bang. The galaxy is similar in many ways to GNZ11, which we have discussed in previous evenings. The galaxy shows evidence for a substantial central supermassive black hole, in addition to the unusual stellar population properties that characterize the broader sample. The detailed properties are, by every careful description, characteristic of the broader population of impossible early galaxies. The sixth galaxy is Sears 1019. The galaxy was identified through Sears observations and is at a redshift of approximately 8.7, corresponding to a cosmic age of approximately 600 million years after the Big Bang. The galaxy is somewhat closer than the previous examples, but still substantially more massive and more evolved than the standard framework predicts for its cosmic epoch. The galaxy shows evidence for substantial chemical enrichment, organized dynamical structure, and a central supermassive black hole. The galaxy is, by every careful estimate, a particularly clean example of how the early universe was producing galaxies that should not have existed yet. The seventh galaxy is JADES GS Z14-1. The galaxy was identified through JD's observations and is at a redshift of approximately 13.9, corresponding to a cosmic age of approximately 290 million years after the Big Bang. The galaxy is similar in many ways to JD's GS Z14-0, but at slightly different position and with somewhat different observational properties. The galaxy is, by every careful estimate, additional confirmation that the impossible galaxy phenomenon is not limited to a few unusual examples, but is a broader pattern across the early universe. The cumulative catalogue of impossible early galaxies is, by every careful description, growing rapidly. The total number of confirmed examples is, by every careful estimate, now in the hundreds. The individual examples we have just discussed are the most striking, but the broader population shows similar patterns at less extreme levels. The contradictions with the standard framework are, by every careful estimate, real and statistically robust. The next sections of our conversation tonight will look at the specific observational evidence in more detail and at the theoretical proposals for accommodating the observations. Let's spend more time on JWST Z14-0 specifically, because the galaxy is, by every careful description, the most striking individual example we have of the impossible early galaxy phenomenon. The detailed properties of this single galaxy provide, by every careful estimate, particularly clean observational tests of the various theoretical interpretations. Tonight, we will work through what we know about JWST Z14-0 in detail. The galaxy was first identified through deep JWST imaging in the JWST survey field. The initial photometric observation suggested a candidate galaxy at a very high redshift. But photometric redshifts have, by every careful estimate, substantial uncertainties at the highest redshifts. The definitive confirmation required spectroscopic follow-up. The spectroscopic follow-up was performed with the JWST near-infrared spectrograph. The detailed observations were led by Stefano Carniani at the Scuola Normale Superiore in Pisa, with collaborators from the broader JWST team. The observations confirmed the high redshift candidate with a measured redshift of 14.32. The redshift corresponds to a cosmic age of approximately 290 million years after the Big Bang. The detailed spectroscopic observations have revealed the specific properties of the galaxy. The galaxy is unambiguously at high redshift. The redshift is, by every careful estimate, the highest ever spectroscopically confirmed for any galaxy. But the more striking aspects of the observations are not the redshift itself. They are the specific properties of the galaxy at this extreme cosmic epoch. The estimated stellar mass is approximately 100 million solar masses. The mass is, by every careful description, far larger than the standard framework predicts for galaxies at this cosmic age. The framework predicts, for a galaxy at redshift 14, a typical stellar mass of approximately 1 million solar masses. The observed mass is approximately 100 times larger. The detailed mass estimate has been refined through subsequent analyses by various research groups. The team led by Mike Boylan-Colchin at the University of Texas has produced detailed independent mass estimates. The team led by Sandro Tacella at the University of Cambridge has produced complementary estimates. The teams use slightly different stellar population models and slightly different analysis approaches, but the cumulative results are, by every careful description, consistent with the original Carniani estimate within the systematic uncertainties. The galaxy is genuinely much more massive than the framework predicts. The detailed spectroscopic observations also reveal the chemical composition of the gas. The spectrum shows emission lines from oxygen, hydrogen, and various other elements. The line ratios provide direct measures of the gas metallicity. The measured metallicity is, by every careful estimate, approximately 1/10 of the local universe values. The metallicity is, by every careful description, substantially higher than the framework predicts for galaxies at this cosmic age. The framework predicts essentially pristine gas compositions at redshifts greater than 10. The observed metallicity requires substantial chemical enrichment to have already occurred by the cosmic age at which we observe the galaxy. The implications for the timing of stellar nucleosynthesis are substantial. The galaxy's stars must have already lived through complete evolutionary cycles. The first stars must have formed at cosmic ages substantially earlier than the framework predicts. The cumulative timing requires, by every careful estimate, substantial modifications to the standard early universe physics. The detailed morphological properties of the galaxy have also been characterized. The galaxy is, by every careful description, marginally resolved in the JWST images. The intrinsic physical size is approximately 1 kiloparsec. Far smaller than typical local universe galaxies, but larger than the framework predicts for galaxies at this cosmic epoch. The shape of the galaxy is, by every careful estimate, somewhat asymmetric, suggesting ongoing dynamical evolution, but the galaxy is also organized enough to be classified as a coherent structure, rather than as a chaotic ensemble of star-forming regions. The detailed kinematics of the galaxy have been partially constrained by the spectroscopic observations. The emission line widths provide some information about the internal velocity dispersions. The line widths suggest, by every careful estimate, that the galaxy has internal velocities consistent with its inferred mass. The galaxy is gravitationally self-consistent in this sense, but more detailed kinematic constraints will require, by every careful description, additional observations with higher spectroscopic resolution. The cumulative properties of JWST Z1410 are, by every careful description, what makes the galaxy such a striking example. The galaxy is too massive, too chemically enriched, too organized and too dynamically mature for the standard framework predictions at its cosmic epoch. The combined evidence is, by every careful estimate, substantially beyond what the framework can accommodate without substantial modifications. The detailed follow-up observations of JWST Z1410 are continuing. The Atacama Large Millimeter Array has performed millimeter observations of the galaxy that provide additional information about the dust and cold gas content. The Hubble Space Telescope archive has been searched for any pre-JWST detections of the galaxy. The combined multi-wavelength data are, by every careful estimate, providing increasingly detailed constraints on the galaxy's properties. The detailed picture is, by every honest description, gradually emerging. Let's now look in more detail at the specific observational evidence that creates the contradictions with the standard framework. The evidence has, by every careful description, several specific components that each independently challenge the framework. The first component is the mass problem. The galaxies at the highest redshifts are, by every careful estimate, far more massive than the standard framework predicts. The detailed evidence for the mass problem comes from spectral energy distribution fitting. The technique involves comparing the observed spectra of distant galaxies to model spectra produced by populations of stars with specific masses, ages, and metallicities. The best fit model parameters provide estimates of the galaxy's total stellar mass, average stellar age, and chemical composition. The technique has been used extensively for galaxies at lower redshifts and is, by every careful description, reasonably well validated. The detailed application of the technique to the highest redshift JWST galaxies produces stellar mass estimates that are, by every careful measurement, substantially larger than the standard framework predicts. The estimates depend on the specific stellar population models used, but the general pattern is consistent across different modeling approaches. The galaxies have stellar masses approximately 10 to 100 times larger than the framework predicts for their cosmic ages. The discrepancy is, by every careful description, not subtle. It is, by every careful estimate, factors of 10 to 100 in the relevant quantitative measures. The detailed cosmic timeline of the problem is, by every careful description, what makes it striking. The standard framework predicts that stellar mass should build up gradually over cosmic time, with most of the mass accumulating during the first few billion years through ongoing star formation. The framework predicts that galaxies at cosmic ages of approximately 300 million years after the Big Bang should have stellar masses of approximately 1 million solar masses. The observed galaxies have stellar masses of approximately 100 million to 1 billion solar masses. The discrepancy is, by every careful estimate, far larger than the systematic uncertainties in the mass estimation technique. The detailed implications for the cosmic timeline are, by every careful description, substantial. The galaxies must have either formed stars much faster than the framework predicts, or they must have started forming earlier than the framework predicts, or both. The detailed quantitative requirements for the modifications are, by every careful estimate, substantial. The galaxies must have been forming stars at rates approximately 10 to 100 times higher than the framework predicts. The galaxies must have started forming stars at cosmic ages of approximately 50 to 100 million years after the Big Bang, far earlier than the framework predicts. The combined modifications are, by every careful description, what is required to accommodate the observations. The detailed comparison between the observations and the framework predictions has been performed by various research groups. The teams led by Mike Boylan-Colchin at the University of Texas at Austin, Ivo Labe at Swinburne University, Joel Leger at Pennsylvania State University, and others have all produced detailed comparisons. The comparisons confirm, by every careful estimate, that the mass discrepancy is real and statistically robust. The discrepancy is not, by every careful description, an artifact of the mass estimation technique or the specific stellar population models used. The detailed analysis has been particularly thorough because the implications for cosmology are so substantial. If the masses are real, the standard framework requires substantial modification. The careful checking of the analysis has been, by every careful estimate, repeatedly performed, and the conclusions have been repeatedly confirmed. The galaxies really are too massive for their cosmic ages. The detailed cosmological implications of the mass problem are, by every careful description, significant. The framework predicts the cosmic abundance of dark matter, halos of various masses at each cosmic epoch. The framework predicts that the most massive halos at very early cosmic epochs should host the most massive galaxies. The framework predicts specific quantitative relationships between halo mass, galaxy mass, and cosmic time. The observations are, by every careful estimate, inconsistent with the standard relationships. The galaxies are too massive for the predicted halo abundances at their cosmic epochs. The implications are, by every careful description, that either the halo abundances are different from what the framework predicts, or the galaxy formation efficiency in early halos is much higher than the framework predicts, or both. The detailed modifications required to accommodate the observations are, by every careful estimate, substantial. They cannot be small perturbations to the standard framework. They require, by every careful description, substantial changes to specific aspects of the framework. The next sections of our conversation tonight We'll look at the specific proposals for these changes. The proposals are, by every careful estimate, still being actively developed. The detailed picture is, by every honest description, still being worked out. But the broad outlines are becoming reasonably clear. The early universe was producing galaxies that the standard framework, in its simplest form, cannot accommodate. The framework requires modification. The second component of the contradictions is the age problem. The galaxies at the highest redshifts have, by every careful measurement, stellar populations that appear older than the standard framework predicts. The age problem is, by every careful estimate, distinct from the mass problem and provides independent evidence that the framework requires modification. The detailed evidence for the age problem comes from the same spectral energy distribution fitting that we discussed for the mass problem. The technique provides estimates of the average stellar age of the galaxy's population, in addition to the total stellar mass. The age estimates depend on specific spectral features that are sensitive to the age distribution of the stars. Young stellar populations have specific spectral signatures that are different from older stellar populations. The detailed differences allow age estimates with reasonable precision. The detailed application of the technique to the highest redshift, JWST galaxies, produces age estimates that are, by every careful measurement, surprisingly old. The galaxies appear to have, in many cases, average stellar ages of approximately 200 to 400 million years. The cosmic ages of the galaxies at their observed redshifts are, by every careful estimate, only approximately 300 to 500 million years. The galaxies appear, in this sense, to have stellar populations that are nearly as old as the universe at the time we observe them. The implication is, by every careful description, substantial. The galaxies must have started forming stars essentially at the earliest possible cosmic epoch and must have continued forming them throughout the available cosmic time. But the standard framework predicts that significant star formation should not begin until at least 100 to 200 million years after the Big Bang. The framework predicts that even the earliest galaxies should have stellar populations that are substantially younger than the cosmic age available. The observed age distributions are, by every careful estimate, inconsistent with the framework predictions. The most striking individual examples have stellar populations that appear, by every careful description, marginally older than the cosmic age at the observed redshift. The discrepancy is small but real. The galaxies appear in specific quantitative ways to have lived through more cosmic time than was available between the Big Bang and the time we observe them. The implication is, by every careful estimate, that some aspect of the standard analysis must be wrong. Either the age estimates are systematically too old, or the cosmic age calculations are systematically too small, or some combination of both. The detailed investigation of these possibilities has been performed by various research groups. The teams have considered, by every careful description, various sources of systematic uncertainty in the age estimation technique. The systematics include the specific stellar population models used, the chemical composition assumed for the stars, the dust extinction model applied, and various other aspects. The detailed investigation suggests, by every careful estimate, that the systematic uncertainties are substantial but not large enough to fully explain the age problem. The galaxies really do appear to have stellar populations that are, in many cases, marginally older than the cosmic age available. The implications for the standard cosmological framework are, by every careful description, profound. If the galaxies really are older than the cosmic age, the standard timeline of cosmic history is wrong. The Big Bang would have happened earlier than the standard framework predicts. The age of the universe would be larger than the standard framework predicts. The Hubble constant would be smaller than the local universe measurements suggest. These are, by every careful estimate, substantial modifications to the standard cosmological framework. The detailed comparison between the age estimates and the cosmological framework has, by every careful description, generated substantial discussion in the research community. Some research groups have argued that the age problem reflects substantial systematic uncertainties that future observations will resolve. Others have argued that the age problem reflects substantial modifications to the standard framework that future observations will confirm. The detailed resolution is, by every honest description, still being worked out. The detailed analysis of individual galaxies has been particularly important. The team led by Mike Boylan-Colchin at the University of Texas has produced detailed analyses of the age estimates for several of the most striking individual examples. The analyses confirm, by every careful estimate, that the ages are old but with substantial systematic uncertainties. The uncertainties allow, in some cases, ages that are consistent with the standard framework, but only at the edges of the uncertainty range. The central estimates are, by every careful description, persistently older than the framework predicts. The pattern is, by every careful estimate, real and consistent across the population. The detailed implications continue to be worked out. The next sections of our conversation tonight will look at the additional observational evidence that compounds the mass and age problems. The combined evidence is, by every careful description, what has driven the current substantial revision of the standard framework. The third component of the contradictions is the morphology problem. The galaxies at the highest redshifts have, by every careful observation, organised structural features that the standard framework predicts should not have had time to develop. The morphology problem is, by every careful estimate, particularly striking because it is directly visible in the JWST images. The detailed morphological observations are, by every careful description, what give the broader contradictions a visually intuitive character. The standard framework predicts that the earliest galaxies should be morphologically irregular. The dynamical conditions in the early universe, with rapid gas inflows and mergers happening frequently, are not conducive to the formation of organised structures. The earliest galaxies should look chaotic in the standard framework. They should have multiple bright knots of star formation distributed irregularly across the galaxy. They should show evidence of recent mergers with disturbed kinematic structures and asymmetric brightness distributions. The morphological predictions are, by every careful estimate, what the standard framework requires for galaxies at very early cosmic epochs. The observed morphologies from JWST are, by every careful description, substantially different from the predictions. Many of the highest redshift galaxies show organised disk structures, with smooth brightness distributions and rotational symmetry. The disk structures should not, by every careful estimate, have had time to develop. The formation of a disk requires the gas in the galaxy to settle into an organised rotating configuration, which requires substantial cosmic time. The earliest galaxies in the standard framework should be too young for disks to have formed. The observed disks are, by every careful description, particularly striking. The team led by Stephanie Juneau at the National Optical Astronomy Observatory has performed detailed morphological analyses of high redshift JWST galaxies. The analyses identify, by every careful estimate, substantial fractions of the galaxies as having organised disk morphologies. The fraction increases with cosmic time, as the framework predicts. But the absolute fraction at the earliest cosmic epochs is, by every careful description, far larger than the framework predicts. The galaxies should be mostly irregular at the highest redshifts. They are not. The detailed properties of the observed disks are also informative. The disks have, by every careful measurement, substantial rotational velocities. The rotational velocities provide direct measures of the dynamical maturity of the galaxies. The team, led by Reinhard Genzel at the Max Planck Institute for Extraterrestrial Physics, has measured rotational velocities for several high redshift JWST galaxies. The measurements show, by every careful estimate, rotational velocities of approximately 100 to 200 kilometers per second. The velocities are characteristic of substantially evolved disk galaxies, not of the chaotic early structures the framework predicts. The morphology problem is, by every careful description, not limited to the most extreme examples. The broader population of high redshift JWST galaxies shows, by every careful measurement, systematically more organized morphologies than the framework predicts. The pattern is consistent across different surveys and different research groups. The teams led by Sandro Tacella at the University of Cambridge, Stephen Finkelstein at the University of Texas, and others have all reported similar patterns. The cumulative evidence is, by every careful estimate, substantial. The detailed implications for the dynamical evolution of galaxies are, by every careful description, substantial. The framework predicts specific timescales for the formation of disks, the development of rotational dynamics, and the establishment of organized galactic structure. The observations are, by every careful estimate, inconsistent with these timescales. The galaxies are reaching dynamical maturity faster than the framework predicts. The detailed mechanisms for the accelerated dynamical evolution are, by every careful description, an active area of investigation. Some research groups have proposed that the dark matter dynamics in the early universe are different from what the framework predicts. Others have proposed that the gas dynamics are different. Others have proposed that the feedback from supernovae and stellar winds is different. The detailed proposals are, by every careful estimate, still being developed. The connection between the morphology problem and the other components of the broader contradictions is, by every careful description, important. The morphology problem, the mass problem, and the age problem are not independent. They are, by every careful estimate, different aspects of the same underlying phenomenon. The galaxies in the early universe were forming faster, growing larger, aging more rapidly, and organizing into disks earlier than the standard framework predicts. The combined evidence is, by every careful description, what has driven the broader theoretical reconsideration. The framework requires substantial modification to accommodate all of these aspects simultaneously. The next sections of our conversation tonight will look at the proposed modifications to the framework. The proposals are, by every careful estimate, still being developed. The detailed picture is, by every honest description, still being worked out. Let's spend more time on the disk structures observed in the early JWST galaxies. The disk structures are, by every careful description, particularly striking, because they are directly visible in the JWST images. The detailed properties of these disks provide, by every careful estimate, some of the cleanest tests of the various theoretical interpretations. Tonight, we will work through what we know about early disk formation in detail. The standard framework predicts that disk formation requires specific cosmic conditions. The gas in a forming galaxy must, by every careful description, settle into an organized rotating configuration, with most of the angular momentum oriented in a common direction. The settling requires substantial cosmic time. The gas must lose energy through dissipation processes while preserving its angular momentum. The cumulative effect is gradual convergence toward a stable disk geometry, but the cosmic time available at the highest redshifts is, by every careful estimate, very limited. The framework predicts that galaxies at redshifts greater than 10 should be in the chaotic pre-disk phase, with gas distributions that are irregular and rapidly evolving. The detailed observations from JWST are, by every careful description, substantially different from the predictions. Multiple research groups have identified specific high redshift galaxies that show clear disk morphologies. The disk structures have been confirmed through detailed analyses of the JWST images by various teams. The team led by Stephanie Juno at the National Optical Astronomy Observatory has performed systematic morphological analyses of large samples of high redshift galaxies. The team led by Sandro Ticella at Cambridge has performed complementary analyses with detailed structural modelling. The cumulative results show, by every careful estimate, that disk fractions are substantially higher than the standard framework predicts. The detailed properties of the observed disks have also been characterized. The disks have, by every careful measurement, characteristic sizes of approximately 1 to a few kiloparsecs at redshifts of 10 and higher. The sizes are smaller than typical local universe disks, but larger than the standard framework predicts for galaxies at these cosmic epochs. The disks have characteristic rotational velocities of approximately 100 to 200 kilometers per second. The rotational velocities are sufficient to dominate the dynamical support of the disks, indicating substantial dynamical maturity. The disks have, by every careful description, organized brightness distributions with smooth radial profiles and minimal asymmetry. The detailed kinematic measurements have been performed by various groups. The team led by Reinhard Genzel at the Max Planck Institute has used integral field spectroscopy to measure detailed velocity fields for several high redshift galaxies. The measurements reveal, by every careful estimate, organized rotational patterns that are characteristic of substantially evolved disks. The patterns are not what the standard framework predicts, but they are real. The detailed implications for early galaxy formation are substantial. The disks must have formed faster than the framework predicts. The angular momentum must have organized earlier in cosmic history. The detailed mechanisms for the accelerated disk formation are, by every careful description, an active area of investigation. Various theoretical proposals have been developed. The first proposal involves enhanced gas inflow with preferred angular momentum directions. If the gas inflows into the early dark matter, halos have systematically aligned angular momentum. The disks could form rapidly without requiring lengthy dissipation processes. But the detailed predictions for aligned inflows depend on the cosmic structure formation, and the predictions are difficult to test directly. The second proposal involves enhanced dissipation mechanisms in early gas. If the gas in early galaxies could lose energy faster than the standard framework predicts, the settling into disks could happen on shorter timescales. But the specific physical mechanisms for enhanced dissipation are, by every careful estimate, not yet fully understood. The third proposal involves different dark matter dynamics in the early universe. If the dark matter behavior at very small scales differs from the standard predictions, the dynamical conditions for disk formation could be different. But the detailed dark matter modifications are, by every careful description, constrained by other observations. The detailed reconciliation between the observed early disks and the various theoretical proposals is, by every careful estimate, ongoing. The current best understanding is that some combination of modifications to the standard star formation physics and possibly modifications to the dark matter dynamics is required, but the detailed picture is, by every honest description, still being worked out. The continuing observations with JWST and the future ELT will, by every careful estimate, substantially refine the picture. The detailed morphological and kinematic properties of larger samples of early galaxies will, by every careful description, definitively test the various theoretical proposals. The work is, by every honest description, in active progress. The detailed mechanisms for the accelerated early disk formation will, by every careful estimate, gradually emerge from the combined observational and theoretical work over the next several years. The fourth component of the contradictions is the chemistry problem. The galaxies at the highest redshifts show, by every careful measurement, substantial enrichment with heavy chemical elements that the standard framework predicts should not yet exist in the available cosmic time. The chemistry problem is, by every careful estimate, perhaps the most striking of all the components because it touches directly on the cosmic timeline of stellar nucleosynthesis. The standard framework predicts specific things about the chemical evolution of the early universe. The Big Bang nucleosynthesis produces, in the first few minutes after the Big Bang, primarily hydrogen and helium with traces of lithium. The subsequent chemical enrichment requires stellar nucleosynthesis. Stars must form, evolve through their lives, and die as supernovae or planetary nebulae. The dying stars release the heavier elements produced in their interiors into the surrounding gas. The released elements must then mix with the gas, providing the raw material for subsequent generations of stars. The cumulative process takes substantial cosmic time. The framework predicts that the chemical enrichment at very early cosmic epochs should be, by every careful estimate, very small. The galaxies at redshifts greater than 10 should have metallicities approximately 1/100th to 1,000th of the local universe values. But the observed metallicities are, by every careful measurement, substantially higher than the framework predicts. The galaxies have metallicities approximately 1/10th to 1/3 of the local universe values. The discrepancy is, by every careful description, factors of 10 to 100 above the framework predictions. The detailed measurements of metallicity come from the spectroscopic emission lines of specific heavy elements. The oxygen, neon, and carbon emission lines are particularly useful because they are produced by gas that is photoionized by hot young stars. The line ratios provide direct measures of the chemical composition of the gas. The team led by Tobias Lucer at the University of Cambridge has performed detailed metallicity measurements for several of the most distant JWST galaxies. The team led by Roberto Maiolino, also at Cambridge, has performed complementary measurements with substantial care to systematic effects. But the measurements have, by every careful estimate, consistently shown metallicities that are substantially higher than the framework predicts. The implications for the cosmic timeline are, by every careful description, substantial. The metallicities require either much earlier and faster stellar nucleosynthesis than the framework predicts, or modified mechanisms for producing heavy elements that operate without requiring multiple generations of stars or both. The detailed cosmic timeline for stellar nucleosynthesis is, by every careful estimate, what creates the problem. The first stars must form. They must evolve through their lives, which takes typically tens of millions of years for the most massive stars. They must die and release their heavy elements. The released elements must mix with the surrounding gas. Subsequent generations of stars must then form from the enriched gas. The cumulative process requires, by every careful description, hundreds of millions of years, even under the most optimistic assumptions. But the observed cosmic age available for this process at redshifts of 14 is only approximately 300 million years. The framework cannot, by every careful estimate, produce the observed metallicities in the available cosmic time. Some modification is required. The detailed proposals for modifying the framework include several specific possibilities. The first possibility is that the first generation of stars formed earlier than the framework predicts. The population 3 stars would have to start forming at cosmic ages of approximately 50 to 100 million years, far earlier than the framework predicts. But the conditions for early population 3 formation are, by every careful description, restrictive. The cosmic gas must be sufficiently cool to collapse into stars. The cooling requires specific molecular hydrogen cooling channels that are, by every careful estimate, only available in specific cosmic conditions. The second possibility is that the first generation of stars was substantially more massive than the framework predicts. Massive stars produce heavy elements much faster than typical stars, both because they evolve faster and because they produce more heavy elements per unit stellar mass. Top-heavy initial mass functions, where the typical stellar mass is approximately 100 to 1,000 solar masses, would substantially accelerate the chemical enrichment. But the detailed predictions for the metallicity patterns produced by top-heavy initial mass functions are, by every careful estimate, specific. They predict particular ratios of different chemical elements that should match the observations. The current best comparisons are, by every careful description, encouraging, but not yet definitive. The third possibility is that the chemical enrichment is local to the regions around the most massive stars and does not reflect the broader gas environment. The interpretation proposes that the observed metallicities reflect, by every careful estimate, the immediate environments of specific star-forming regions rather than the average gas composition. The detailed implications would mean that the broader gas is less enriched than the spectroscopic measurements suggest. But the detailed observational tests of this possibility are, by every careful description, ongoing, and the conclusions are not yet definitive. The chemistry problem continues to be, by every careful estimate, one of the most active areas of investigation in the broader early universe astrophysics. Let's now look at the proposed theoretical explanations in more detail. The first major proposal is accelerated early star formation. The proposal suggests that star formation in the very early universe was substantially more efficient than the standard framework predicts. The first generations of stars formed earlier, in larger numbers, and produced more heavy elements per unit cosmic time than the framework currently assumes. The detailed implementation of accelerated early star formation involves several specific mechanisms. The first mechanism is enhanced gas cooling in the early universe. The standard framework assumes that the cooling of pristine gas in the first dark matter halos is limited by the available molecular hydrogen cooling channels. The cooling is, by every careful estimate, slow compared to what is required to form stars rapidly, but various theoretical groups have proposed that additional cooling mechanisms operated in the early universe. The cooling could be enhanced by every careful description, the presence of trace amounts of lithium hydride, deuterium, substituted molecules, or specific atomic line transitions that operate at very low temperatures. The enhanced cooling would allow gas to collapse and form stars more rapidly than the standard framework predicts. The second mechanism is enhanced gas inflow into early dark matter halos. The standard framework predicts specific rates for the inflow of cosmic gas into the dark matter halos that host the first galaxies. The rates depend on the cosmic dark matter dynamics and the gas thermodynamics. The framework predicts inflow rates that, in the standard interpretation, limit the maximum star formation rates achievable in the early universe. But various theoretical groups have proposed that the inflow rates are actually substantially higher than the standard predictions. The proposals suggest that the cosmic gas dynamics in the early universe were different from the framework assumptions. The differences could be due to, by every careful estimate, modifications to the dark matter dynamics, modifications to the gas thermodynamics, or modifications to the cosmic geometry. The third mechanism is enhanced star formation efficiency in early gas clouds. The standard framework assumes that only a small fraction of the gas in a star-forming region actually converts to stars. The fraction is, by every careful description, approximately 1 to 5% in typical local universe conditions. But various theoretical groups have proposed that the efficiency was substantially higher in the early universe. The enhanced efficiency could be due to, by every careful estimate, the absence of dust grains that normally trigger gas cooling and fragmentation, the absence of heavy elements that normally limit further star formation through feedback, or the specific dynamical conditions of the early universe. The detailed quantitative predictions of accelerated early star formation have been worked out by various research groups. The teams led by Jeremy Baruzzi at the University of Arizona, Aaron Smith at MIT, and others have produced detailed simulation predictions. The predictions show that accelerated early star formation can, by every careful estimate, accommodate substantial fractions of the observed JWST galaxy properties. But the predictions also have specific signatures that can be tested against the observations. The signatures include the detailed shape of the cosmic star formation history, the detailed distribution of stellar properties across the galaxy population, and the specific chemical abundance patterns that should appear in the early galaxies. The detailed comparisons between the accelerated early star formation predictions and the JWST observations are, by every careful description, encouraging but not yet definitive. The framework can accommodate the broad observational properties, but the detailed quantitative match is still being refined. Different research groups have proposed different specific implementations that produce slightly different predictions. The detailed identification of which implementation is correct is, by every careful estimate, an active area of investigation. The implications of accelerated early star formation for the broader cosmological framework are, by every careful description, significant. If the framework is modified to include accelerated early star formation, the cosmic timeline of structure formation shifts substantially. The cosmic dawn, the epoch during which the first stars and galaxies illuminated the previously dark universe, happens earlier than the standard framework predicts. The cosmic rionization, the subsequent epoch during which the early starlight ionized the surrounding hydrogen gas, happens earlier and proceeds more rapidly. The cosmic chemical enrichment, the broader process by which heavy elements spread throughout the universe, accelerates substantially. The combined modifications produce, by every careful estimate, a substantially different picture of how the early universe operated. But the detailed picture is, by every honest description, still being worked out. The proposal is currently the leading explanation for the JWST observations among the various theoretical alternatives, but other proposals continue to be developed. The detailed comparison between the alternatives requires, by every careful estimate, additional observational and theoretical work. The next sections of our conversation tonight will consider the alternative proposals. The second major proposal is a top-heavy initial mass function. The proposal suggests that the typical stellar masses in the early universe were substantially larger than in the local universe. The first generations of stars were dominated by massive stars rather than by the lower mass stars that dominate the local stellar populations. The detailed implications of a top-heavy initial mass function are, by every careful estimate, substantial for the observed properties of early galaxies. The initial mass function is, by every careful description, the distribution of stellar masses that emerges from a star formation event. The standard initial mass function in the local universe, called the Krupa or Salpeter initial mass function depending on the specific formulation, has substantial numbers of low-mass stars and only small numbers of high-mass stars. The typical stellar mass is approximately half a solar mass, but various theoretical groups have proposed that the initial mass function was substantially different in the early universe. The proposal is that the typical stellar mass was approximately 10 to 100 solar masses, far higher than the local universe value. The detailed reasons for the proposed top-heavy initial mass function involve specific aspects of the early universe physics. The first reason is the absence of dust grains in the early universe. Dust grains, by every careful estimate, play important roles in cooling gas and triggering fragmentation in star-forming clouds. In the absence of dust, the cooling is less efficient and the gas tends to collapse into larger structures. The second reason is the absence of heavy elements in the early universe. Heavy elements, by every careful description, also contribute to cooling and to opacity in star-forming clouds. In their absence, the gas dynamics is different and the resulting stellar masses are different. The third reason is the higher temperature of the cosmic microwave background in the early universe. The microwave background, by every careful estimate, sets a temperature floor that affects how cold gas can become. The higher floor in the early universe limits how cool gas can collapse, which affects the typical stellar masses. The combined effect of these factors is, by every careful description, what produces the proposed top-heavy initial mass function. The detailed observational consequences of a top-heavy initial mass function are specific. The first consequence is enhanced chemical enrichment per unit star formation. Massive stars produce far more heavy elements per unit stellar mass than typical stars. A top-heavy initial mass function would, by every careful estimate, produce substantially more chemical enrichment per unit star formation than the standard initial mass function. The enhanced enrichment matches, by every careful description, the observed metallicities in the JWST galaxies reasonably well. The second consequence is enhanced ultraviolet luminosity. Massive stars produce most of the ultraviolet light from a galaxy. A top-heavy initial mass function would produce substantially more ultraviolet light per unit stellar mass. The enhanced ultraviolet matches, by every careful estimate, the observed brightnesses of the JWST galaxies reasonably well. But the third consequence is that the stellar mass estimates from the standard spectral energy distribution fitting would be systematically too high. The standard fitting assumes the local universe initial mass function. If the actual initial mass function is top-heavy, the fitting would attribute the observed light to substantially more stars than are actually present. The detailed implications of this systematic effect have been worked out by various research groups. The team, led by Charlie Conroy at Harvard, has produced detailed analyses of how the mass estimates would shift if the initial mass function were top-heavy. The analyses suggest, by every careful estimate, that the mass estimates could be too high by factors of 3 to 10 under specific top-heavy scenarios. The implication is, by every careful description, that the mass problem we discussed earlier may be partially resolved by a top-heavy initial mass function. The galaxies are not as massive as the standard analysis suggests. They just appear that bright because their stellar populations are weighted toward the most luminous, massive stars. The detailed observational tests of the top-heavy initial mass function are, by every careful description, ongoing. The specific predictions for the chemical abundance ratios, the detailed shapes of the spectral energy distributions, and the detailed time evolution of the stellar populations all provide tests. The current best estimates from these tests are, by every careful estimate, encouraging for the top-heavy hypothesis, but not yet definitive. The implications for the broader cosmological framework are, by every careful description, less radical than for the accelerated star formation proposal. The top-heavy initial mass function does not require substantial modifications to the basic cosmological framework. It only requires modifications to the specific assumptions about how stars formed in the early universe. The standard framework continues to apply, with refinements to specific aspects. The detailed picture continues to be developed. The next sections of our conversation tonight will consider the more radical alternatives that have been proposed. Let's spend more time on the question of population 3 stars and what they would look like if we could observe them directly. Population 3 stars are, by every careful description, the hypothesized first generation of stars in the universe. They are predicted to have formed from pristine gas with essentially no heavier elements. Their properties are predicted to be substantially different from any stars we currently observe. The detailed characterization of population 3 stars is, by every careful estimate, central to understanding the cosmic timeline of stellar nucleosynthesis. Tonight, we will work through what the standard framework predicts about these stars and what the JWST observations might be revealing about them. The standard framework predicts that population 3 stars formed in the first dark matter halos in the cosmic universe approximately 100 to 200 million years after the Big Bang. The stars formed from gas that was, by every careful estimate, composed almost entirely of hydrogen and helium with traces of lithium. The absence of heavier elements has substantial consequences for how the stars form and what properties they have. The first consequence is that the cooling of the gas is, by every careful description, slower than for gas, with heavier elements. Heavy elements provide important atomic cooling pathways that allow gas to lose heat efficiently. Without them, the gas can only cool through molecular hydrogen pathways, which are less efficient at low temperatures. The slower cooling means that the gas cannot collapse as rapidly as in later cosmic epochs. The second consequence is that the gas tends to collapse into larger structures than in later cosmic epochs. The framework predicts that the typical population 3 star has a mass of approximately 100 solar masses. But the prediction has substantial uncertainty. Different theoretical groups have proposed population 3 masses ranging from approximately 10 solar masses to approximately 1,000 solar masses. The detailed mass distribution depends on the specific cooling pathways available and the specific dynamical conditions in the early universe. The third consequence is that the population 3 stars are predicted to have, by every careful estimate, substantially different evolutionary tracks from later stars. The high masses mean that the stars evolve very rapidly. They exhaust their nuclear fuel within a few million years. They die through powerful supernova explosions or, in some cases, through direct collapse to black holes without significant supernova activity. The detailed evolution depends on the specific stellar mass. The observational signatures of population 3 stars are, by every careful description, distinct. The stars would produce spectra dominated by hydrogen and helium emission and absorption lines, with essentially no signatures of heavier elements. The stars would produce, by every careful estimate, extremely high ultraviolet luminosities relative to their masses, because the high temperatures characteristic of massive stars produce most of their light in the ultraviolet. The stars would have specific chemical abundance ratios in any heavier elements they did produce, characteristic of the specific population 3 supernova nucleosynthesis. The detailed signatures have, by every careful description, been searched for extensively in JWST observations of early galaxies. The team led by Erica Nelson at the University of Colorado has performed detailed searches for population 3 signatures in JD's galaxies. The team led by Roberto Maiolino at Cambridge has performed complementary searches with the NIR SPEC instrument. But the searches have not, by every careful estimate, produced definitive detections of pure population 3 stellar populations. The early galaxies that JWST observes are, by every careful description, already substantially chemically enriched. The chemical signatures show, by every careful measurement, the contributions of multiple previous stellar generations rather than the pristine signatures predicted for pure population 3. The implications are, by every careful description, that the population 3 stars have already lived and died by the time we observe the galaxies. The cosmic timeline of population 3 stellar evolution is, by every careful estimate, compressed compared to the standard framework predictions. The population 3 stars must have formed earlier, evolved through their lives faster, and produced their chemical enrichment more rapidly than the framework predicts. The detailed observational signatures of the population 3 contribution to the chemical enrichment are, by every careful description, an active area of investigation. Specific chemical abundance ratios are sensitive to the population 3 supernova nucleosynthesis. The ratio should appear in any galaxies where population 3 stars have made substantial contributions to the chemical enrichment. The team led by Volker Brom at the University of Texas has produced detailed predictions for the specific abundant signatures, but the current JWST measurements are, by every careful estimate, not yet precise enough to definitively identify the population 3 contribution in individual galaxies. The next generation telescopes will, by every careful description, provide the required precision. The detailed identification of population 3 chemical signatures will, by every careful estimate, definitively confirm or refute the various theoretical interpretations of the early universe. The continuing work is, by every honest description, in active development. The picture is gradually becoming clearer. The population 3 stars are, by every careful description, real cosmic objects that existed in the very early universe. but the detailed properties and the cosmic timeline of their existence are, by every careful estimate, still being worked out. Beyond the modifications to specific aspects of star formation physics, more radical proposals have been developed to accommodate the JWST observations. These proposals involve modifications to the standard cosmological framework itself. The modifications are, by every careful description, substantially more substantial than the star formation proposals. They would, if confirmed, transform our understanding of how the universe operates at the largest scales. Tonight, we will work through the main proposals carefully. The first cosmological proposal involves modifications to dark matter physics. The standard framework assumes that dark matter is composed of weakly interacting massive particles that interact only through gravity. The particles are, by every careful estimate, expected to be cold, meaning that they move at speeds much slower than the speed of light. The cold dark matter framework has been extensively tested at moderate redshifts and matches the observations remarkably well. But various theoretical groups have proposed that the dark matter is actually different from the standard assumptions. The proposed alternatives include warm, dark matter, where the particles move at intermediate speeds. The proposed alternatives include self-interacting dark matter, where the particles have non-gravitational interactions with each other. The proposed alternatives include fuzzy dark matter, where the particles have very small masses and behave as quantum waves at galactic scales. Each of these alternatives produces different predictions for the formation of structure in the early universe. Some of the alternatives can, by every careful estimate, accelerate the formation of structure and accommodate the JWST observations. But the alternatives also produce specific signatures at other cosmic epochs that can be tested. The current best constraints on dark matter properties from the broader observations are, by every careful description, restrictive. The alternative dark matter models that accommodate the JWST observations also tend to be inconsistent with other observations. The detailed reconciliation is, by every careful estimate, an active area of investigation. The second cosmological proposal involves modifications to dark energy physics. The standard framework assumes that dark energy is a cosmological constant, with constant energy density throughout cosmic history. But various theoretical groups have proposed that the dark energy is actually dynamical, with energy density that changes over cosmic time. The dynamical dark energy could, by every careful estimate, modify the cosmic expansion history in ways that affect the apparent ages and properties of early galaxies. The detailed implementation of dynamical dark energy has been proposed in various forms. The forms include quintessence models, where a scalar field provides the energy density. The forms include modified gravity models, where the underlying theory of gravity is modified rather than introducing new energy components. The forms include various other specific implementations, but the detailed predictions of dynamical dark energy at moderate redshifts are, by every careful description, well constrained by the existing observations. The proposals that accommodate the JWST observations tend to require, by every careful estimate, specific modifications that are at the edges of what the broader observations allow. The detailed reconciliation continues to be investigated. The third cosmological proposal involves modifications to the inflationary epoch at the very beginning of the universe. The standard framework assumes that inflation produced a specific spectrum of density perturbations that subsequently grew into the cosmic structures we observe. The spectrum is, by every careful description, what determines the initial conditions for galaxy formation. But various theoretical groups have proposed that the inflationary spectrum was actually different from the standard predictions. The modifications could include, by every careful estimate, additional power at small scales, additional features at specific scales, or various other deviations from the standard spectrum. Each modification produces different predictions for the formation of structure in the early universe. Some modifications can, by every careful estimate, accelerate the formation of the most massive early structures and accommodate the JWST observations. But the modifications also produce specific signatures in the cosmic microwave background and in the broader cosmic structure that can be tested. The current best constraints from these tests are, by every careful description, restrictive. The detailed reconciliation continues to be investigated. The fourth cosmological proposal involves modifications to the Big Bang nucleosynthesis epoch. The proposal suggests that additional chemical enrichment was produced during the very early cosmic epochs through specific physical processes that the standard framework does not include. The additional enrichment would explain, by every careful estimate, the unusually high metallicities observed in the early galaxies without requiring extensive subsequent stellar nucleosynthesis. But the detailed predictions of additional Big Bang nucleosynthesis are, by every careful description, well constrained by the observed abundances of the light elements like deuterium and helium-3. The proposals that accommodate the JWST observations tend to be, by every careful estimate, inconsistent with the light element observations. The detailed reconciliation is, by every careful description, difficult. The cumulative status of the cosmological proposals is, by every honest description, that they remain possible but are restrictive. The proposals are not, by every careful estimate, the leading explanations for the JWST observations. The leading explanations involve modifications to star formation physics rather than modifications to fundamental cosmology. But the more radical proposals continue to be investigated, and the detailed observational tests continue to be developed. Let's now consider the broader cosmological implications of the JWST observations. The implications extend, by every careful description, far beyond the specific galaxies we have been discussing. They touch on essentially every aspect of how we understand the early universe. The standard framework has been the foundation of cosmology for decades. But the JWST observations are forcing a substantial reconsideration of how that foundation should be applied to the earliest cosmic epochs. Tonight, we will work through the broader implications carefully. The first implication is for the cosmic timeline of structure formation. The standard framework predicts that structure formation proceeded gradually, with the smallest structures forming first and larger structures emerging through subsequent mergers and accretion. The framework predicts specific quantitative rates for each stage of structure formation. But the JWST observations suggest that the structure formation was substantially faster than the framework predicts. The largest galaxies emerged earlier than expected. The chemical enrichment proceeded faster than expected. The dynamical assembly of organized structures happened earlier than expected. The cumulative effect is, by every careful estimate, a substantially accelerated cosmic timeline. The implications extend, by every careful description, throughout the history of the universe. If the structure formation was faster than the framework predicts, the cosmic history at all subsequent epochs is also affected. The local universe galaxies we observe today must have formed through processes that started earlier than the framework predicts. But the local universe galaxies match the standard framework predictions remarkably well. The reconciliation between the early universe acceleration and the local universe consistency is, by every careful estimate, an active area of investigation. The leading current explanation is that the acceleration was specific to the earliest cosmic epochs and slowed down at later times, but the detailed mechanism for the slowdown is, by every careful description, not yet fully understood. The second implication is for the cosmic timeline of rayonization. Cosmic rayonization is the epoch during which the ultraviolet light from the first stars and galaxies ionized the previously neutral hydrogen gas that filled the universe. The standard framework predicts that rayonization happened, by every careful estimate, over a cosmic timeline of approximately 500 million to 1 billion years after the Big Bang. The framework predicts specific quantitative properties for the reionization process, including the spatial structure of the ionized regions and the time evolution of the cosmic neutral fraction. But the JWST observations of the early galaxies suggest that the ionizing photon production was substantially higher than the framework predicts. The cumulative ionizing photons from the early galaxy population would, by every careful estimate, have driven rayonization earlier and faster than the framework predicts. But the observed timeline of rayonization from other observational probes, including the cosmic microwave background and the Lyman alpha forest, is broadly consistent with the standard framework. The reconciliation between the high ionizing photon production from JWST galaxies and the conventional reionization timeline is, by every careful description, another active area of investigation. The third implication is for the cosmic dawn epoch. The cosmic dawn is the very early period during which the first stars and galaxies illuminated the previously dark universe. The standard framework predicts that cosmic dawn happened, by every careful estimate, approximately 100 to 200 million years after the Big Bang. The framework predicts specific quantitative properties for the first generation of stars and the radiation they produced. But the JWST observations suggest that cosmic dawn happened earlier and was more intense than the framework predicts. The first stars must have formed in larger numbers, with higher masses, and at earlier cosmic epochs than the framework predicts. The implications for the radio observations of cosmic dawn, currently being made by various experiments including LOFAR and SKA, are substantial. The fourth implication is for the cosmic chemical evolution. The standard framework predicts a specific history of how heavy elements accumulated in the universe through cosmic time. The framework predicts that essentially all of the heavy elements were produced through stellar nucleosynthesis after the first generation of stars formed. But the JWST observations suggest that substantial chemical enrichment had already occurred by very early cosmic epochs. The cumulative chemical history of the universe is, by every careful estimate, more compressed than the framework predicts. The implications for the chemical compositions of younger galaxies, including our own Milky Way galaxy, are, by every careful description, still being worked out. The fifth implication is for the supermassive black holes at galaxy centers. We have discussed in previous evenings how JWST observations have revealed unexpectedly massive, supermassive black holes at the centers of early galaxies. The new observations of the broader galaxy population suggest that the black holes are part of a broader pattern of accelerated early universe activity. But the connection between the black hole growth and the broader galaxy growth is, by every careful estimate, complex and still being worked out. The detailed coevolution of black holes and galaxies in the early universe was, by every careful description, very different from the relationship observed in the local universe. The combined implications are, by every careful description, that the early universe operated according to substantially different rules than the standard framework predicts. The modifications required are, by every careful estimate, not subtle. They are substantial changes to specific aspects of the framework that will require additional theoretical and observational work to fully understand. But the broad outlines of the modifications are, by every careful description, becoming clear. Let's consider the connection between the impossible early galaxies and the broader cosmological tensions that have been emerging in recent years. The connection is, by every careful description, a particularly important aspect of the JWST observations, because it suggests that the early galaxy puzzle is not an isolated anomaly. It is, by every careful estimate, part of a broader pattern of inconsistencies in the standard cosmological framework. Tonight, we will work through the connections carefully. The Hubble tension is perhaps the most striking of the broader cosmological tensions. The Hubble tension refers to the inconsistency between two different measurements of the Hubble constant, the parameter that describes the current rate of cosmic expansion. The first measurement comes from observations of the cosmic microwave background. The Planck satellite measurements published in 2018 produced a Hubble constant of approximately 67.4 kilometers per second per megaparsec. The measurement has, by every careful estimate, very small statistical uncertainties, but the second measurement comes from observations of supernovae and other distance indicators in the local universe. The SH0ES collaboration, led by Adam Rees at Johns Hopkins University, has measured the local Hubble constant to be approximately 73 kilometers per second per megaparsec. The local measurement has different systematic uncertainties from the cosmic microwave background measurement. The difference between the two measurements is, by every careful description, substantially larger than the combined statistical uncertainties. The tension is real. The detailed implications of the Hubble tension have been actively investigated for the past decade. Various theoretical proposals have been developed to accommodate the tension. The proposals include modifications to dark energy, modifications to dark matter, modifications to early universe physics, and various other specific changes to the standard framework. But each proposal also produces specific signatures that can be tested against other observations. The detailed proposals are, by every careful estimate, increasingly constrained as more observational data accumulate. The connection between the Hubble tension and the impossible early galaxies is, by every careful description, that some of the proposed solutions to the Hubble tension also affect the predicted properties of early galaxies. The proposals that involve modifications to early universe physics are particularly relevant. The early dark energy proposals, in which a substantial dark energy component existed at very early cosmic epochs but subsequently dissipated, would change the cosmic expansion history at early times. The change would affect, by every careful estimate, the cosmic age available for early galaxy formation. The detailed effects could potentially accommodate the impossible early galaxies. But the early dark energy proposals also have specific signatures in the cosmic microwave background and in the broader cosmic structure. The detailed comparison between the predicted signatures and the observations is, by every careful description, an active area of investigation. The current best estimates are that early dark energy can accommodate some of the early galaxy properties, but not all of them simultaneously with the Hubble tension. The detailed picture is, by every honest description, still being worked out. The S8 tension is another major cosmological inconsistency. The S8 tension refers to the inconsistency between cosmic microwave background measurements of the matter density variance and local universe measurements of the same quantity from gravitational lensing observations. The cosmic microwave background measurements suggest a specific value of the matter clustering parameter. The local gravitational lensing measurements suggest, by every careful estimate, a somewhat smaller value. The difference is smaller than the Hubble tension, but still statistically significant. The implications for the cosmological framework are, by every careful description, similar to those of the Hubble tension. Various theoretical proposals have been developed, but the proposals that accommodate the S8 tension also tend to affect, by every careful estimate, the predicted properties of early galaxies. The detailed reconciliation is, by every careful description, an active area of investigation. The cosmic microwave background lensing measurements provide additional constraints. The measurements probe, by every careful estimate, the gravitational lensing of the cosmic microwave background by intervening matter. The detailed measurements provide direct constraints on the matter clustering across cosmic history. The current measurements are, by every careful description, broadly consistent with the standard cosmological framework, but with some specific features that may indicate deviations. The detailed analysis is, by every careful estimate, ongoing. The cumulative picture from all the cosmological tensions is, by every careful description, that the standard framework requires modifications. The modifications must accommodate the Hubble tension, the S8 tension, the impossible early galaxies, and the various other anomalies that have been emerging in recent years. The specific modifications that simultaneously accommodate all of the anomalies are, by every careful estimate, restrictive. Different theoretical groups have proposed different specific combinations of modifications, but no single proposal has, by every honest description, gained universal acceptance. The detailed picture is, by every careful description, still being actively developed. The next decade of observations will, by every careful estimate, substantially clarify which specific modifications are required. Let's now look at the future observations that will refine our understanding of the impossible early galaxies. The current observational status is, by every careful description, encouraging, but incomplete. The JWST has revealed the existence of the impossible galaxies, but the detailed characterization of their properties and the definitive identification of which theoretical framework best explains them requires substantially more observational work. The next several years will be, by every careful estimate, a particularly active period for this area of research. The continuing JWST observations will, by every careful description, produce a substantially expanded catalogue of impossible early galaxies. The current catalogue has hundreds of confirmed examples. The expanded catalogue will, by every careful estimate, reach thousands within the next few years. The expanded catalogue will allow detailed statistical analysis of the population properties. The detailed statistics will provide, by every careful description, much stronger tests of the various theoretical proposals. The leading current explanation, accelerated early star formation with a possibly top-heavy initial mass function, makes specific predictions that the expanded catalogue can test. But the alternative explanations also make specific predictions. The detailed comparison will, by every careful estimate, definitively distinguish between the alternatives. The next-generation ground-based telescopes will provide complementary observations. The extremely large telescope, currently under construction in the Atacama Desert in Chile, will have a 39-meter primary mirror, more than 5 times the size of JWST's mirror. The ELT will provide angular resolution approximately 5 times better than JWST. The first ELT observations are expected in 2028. The giant Magellan telescope, currently under construction in Chile, will have a primary mirror equivalent to a 24.5-meter telescope. The first GMT observations are expected in the late 2020s. The 30-meter telescope, currently planned for either Hawaii or the Canary Islands, will have a 30-meter primary mirror. The first TMT observations are expected in the early 2030s. The combined capabilities will, by every careful description, allow detailed observations of individual impossible early galaxies at higher resolution than JWST can achieve. The detailed observations will reveal, by every careful estimate, the specific stellar populations, the detailed chemical abundance patterns, the specific dynamical structures, and the specific connections to surrounding cosmic environments. The detailed observations will, by every careful description, definitively test the various theoretical interpretations. The future space-based observatories will also contribute substantially. The Roman Space Telescope, scheduled for launch in 2027, will provide wide-field infrared observations that complement the JWST deep observations. Roman will identify, by every careful estimate, many more impossible early galaxy candidates that JWST can then follow up with detailed spectroscopy. The Habitable Worlds Observatory, currently in early planning stages, will eventually provide additional observational capabilities. But the Habitable Worlds Observatory is, by every careful description, more than a decade away from operations. The continuing observations with the Atacama Large Millimeter Array, the Very Large Telescope, the Keck telescopes, the Hubble Space Telescope, and various other facilities will provide complementary multi-wavelength observations. The combined observations will, by every careful estimate, reveal the full multi-wavelength properties of the impossible early galaxies. The detailed multi-wavelength data will provide, by every careful description, much stronger tests of the theoretical interpretations than any single wavelength observations can. The future radio observations of cosmic dawn will provide additional constraints. The square-kilometre array, currently under construction in South Africa and Australia, will eventually provide direct radio observations of the cosmic dawn epoch. The observations will measure, by every careful estimate, the specific radio signatures of the first stars and galaxies. But the observations are, by every careful description, still several years from full operations. The detailed predictions for the radio signatures depend on which theoretical interpretation of the JWST observations is correct. The radio observations will, by every careful estimate, definitively distinguish between the alternatives. The continuing theoretical work will refine the framework predictions in parallel with the observational programs. The theoretical simulations of early galaxy formation are, by every careful description, being continuously updated as new observational data become available. The simulations include increasingly detailed treatment of the relevant physical processes. But the simulations are also, by every careful estimate, limited by computational resources. The next-generation supercomputers will allow simulations with substantially higher resolution and more detailed physical processes. The combined theoretical and observational progress will, by every careful description, substantially clarify the picture over the next decade. The current best understanding is that the impossible early galaxies require modifications to the standard cosmological framework, with the modifications focused primarily on accelerated early star formation and possibly a top-heavy initial mass function. But the detailed picture is, by every honest description, still being worked out. The framework continues to be refined as more observations accumulate. The next several years will be, by every careful estimate, particularly important for the development of the picture. The detailed answer to how the early universe actually produced the impossible galaxies is, by every honest description, still in active development. Let's spend more time on the Nancy Grace Roman Space Telescope and what it will reveal about the impossible early galaxies. The Roman Space Telescope is, by every careful description, one of the most important future missions for the study of cosmic structure. The telescope will provide complementary capabilities to JWST that are essential for understanding the early galaxy population at the statistical level. Tonight, we will work through the specific contributions Roman will make. The Roman Space Telescope is named after Nancy Grace Roman, the NASA astronomer who advocated for the original Hubble Space Telescope mission. The telescope is scheduled for launch in 2027. The mission is, by every careful estimate, the major NASA flagship mission of the coming decade. The telescope has a 2.4-meter primary mirror, the same size as Hubble, but the telescope has a substantially wider field of view than Hubble, approximately 100 times wider. The wider field allows, by every careful description, much more efficient survey observations of large regions of the sky. The telescope is optimized for near-infrared observations, with sensitivity comparable to JWST in the relevant wavelength range. The detailed observational programs for Roman have been developed by the NASA science working groups over the past several years. The programs include 3 major surveys plus various smaller programs. The high-latitude, wide-area survey will, by every careful estimate, image approximately 2,000 square degrees of the sky to substantial depth. The survey will identify, by every careful description, many more impossible early galaxy candidates than JWST has identified to date. The time domain survey will repeatedly observe specific regions to identify variable and transient phenomena. The survey will detect, by every careful estimate, supernovae across cosmic history that provide important constraints on the cosmic expansion rate. The coronagraph imaging survey will use a specialized coronagraph instrument to image exoplanets directly. The survey is more focused on planetary science than cosmology, but will, by every careful description, contribute to the broader understanding of stellar systems. The combined surveys will, by every careful estimate, produce a vastly expanded catalogue of high redshift galaxies. The detailed contributions to the impossible early galaxy puzzle are specific. The Roman Wide Area Survey will identify candidate impossible early galaxies at substantially higher statistical numbers than JWST can achieve. The JWST has, by every careful description, deep but narrow observations. Roman will provide wide and reasonably deep observations. The combined capabilities are complementary. JWST identifies and characterizes individual galaxies in detail. Roman identifies large statistical samples that can be followed up by JWST for detailed characterization. The statistical samples are, by every careful estimate, essential for distinguishing between the various theoretical proposals. The detailed predictions for impossible early galaxies depend on cosmic statistics that require large samples to test. The current JWST samples are, by every careful description, large enough to confirm the existence of the impossible galaxies, but not large enough to distinguish between the detailed, theoretical interpretations. The Roman samples will, by every careful estimate, be sufficient for the detailed statistical tests. The combined JWST plus Roman observations will, by every careful description, provide the most comprehensive census of the early galaxy population that has ever been achieved. The detailed analysis of the combined data will, by every careful estimate, substantially refine our understanding of how the early universe operated, but the analysis will require, by every careful description, substantial computational resources and theoretical modelling. The current best estimates suggest that the analysis will be in active development through the late 2020s and into the 2030s. Beyond the impossible early galaxy puzzle, Roman will contribute to several other areas of cosmology. The supernova survey will provide independent constraints on the Hubble constant from the local universe. The wide area survey will provide direct measurements of the cosmic structure across multiple cosmic epochs. The combined contributions will, by every careful estimate, substantially refine our understanding of the broader cosmological tensions. The detailed implications for the standard framework will, by every careful description, become clearer as the Roman observations accumulate. The mission is, by every careful estimate, scheduled to operate for at least 5 years after its launch. The total science output will be, by every careful description, comparable to or larger than the JWST output over a similar period. The combined JWST plus Roman science return is, by every careful estimate, going to define our understanding of the early universe for the next several decades. But the work to integrate the observations with the theoretical frameworks is, by every honest description, just beginning. The next decade will be a particularly active period for the development of our cosmological understanding. Let's bring all of this together as the night settles deeper around us. The galaxies that James Webb has been finding at the very edge of the observable universe are, by every careful description, behaving in ways that the standard cosmological framework cannot easily accommodate. They appear too massive, they appear too old, they appear too organised, they appear too chemically enriched, they appear, in specific quantitative ways, older than the universe that was supposed to have made them. The contradictions are not subtle. They are, by every careful estimate, factors of 10 to 100 in the relevant quantitative measures. The standard framework, in its simplest form, cannot produce the observed early galaxy population. The framework requires modification. The individual examples we have discussed tonight are, by every careful description, the most striking, specific cases. Jade's GS Z14-0 at a redshift of 14.3, Maisie's Galaxy at a redshift of 11.4, GHZ2 at a redshift of 12.4, GS Z13-1 at a redshift of 13.1, Jade's NS1 at a redshift of 10.6. Sears 1019 at a redshift of 8.7, Jade's GS Z14-1 at a redshift of 13.9. Each galaxy is its own data point. Each galaxy independently challenges the standard framework, but the combined population provides statistical evidence that no individual object can. The cumulative pattern is, by every careful estimate, what has driven the broader theoretical reconsideration that is currently underway. The proposed modifications to the standard framework involve several specific possibilities. The leading explanation is accelerated early star formation, in which the first stars formed earlier and more efficiently than the standard framework predicts. The leading explanation also possibly involves a top-heavy initial mass function in which the typical stellar masses in the early universe were substantially larger than in the local universe. The combined modifications can, by every careful estimate, accommodate the observed properties of the impossible early galaxies, but the detailed, quantitative match continues to be refined as more observations accumulate. More radical modifications to the standard cosmological framework have also been proposed. The modifications include alternative dark matter physics, dynamical dark energy, modifications to inflation, and various other specific changes. The radical modifications can also, by every careful description, potentially accommodate the impossible early galaxies. But the radical modifications are, by every careful estimate, more restrictive when combined with the other observational constraints. The current best estimates favor the star formation modifications over the cosmological modifications, but the picture continues to develop. The connection to the broader cosmological tensions is, by every careful description, real and important. The impossible early galaxies are not an isolated anomaly. They are part of a broader pattern that includes the Hubble tension, the S8 tension, and various other inconsistencies in the standard framework. The cumulative pattern suggests that substantial modifications to the framework are required. The detailed, specific modifications are, by every honest description, still being worked out. The continuing JWST observations, the next-generation ground-based telescopes including the extremely large telescope coming online in 2028, the giant Magellan telescope, the 30-meter telescope, the Roman Space Telescope launching in 2027, the future LISA mission launching in 2035, and various other observational programs will, by every careful estimate, substantially refine our understanding over the next decade. The detailed picture that emerges will, by every careful description, be substantially different from the standard framework predictions, but the broad outlines are already, by every careful estimate, becoming clear. The implications for our broader understanding of the universe are, by every careful description, profound. The early universe was not behaving like a simple continuation of the cosmic history we observe at later epochs. The early universe was, by every careful estimate, operating according to substantially different rules. The galaxies were forming faster, growing larger, organizing into structures earlier, and producing chemical enrichment more rapidly than the standard framework predicts. The cosmic timeline of structure formation was, in this picture, accelerated compared to the standard predictions. The detailed mechanisms for the acceleration are, by every honest description, still being worked out. But the existence of the acceleration is, by every careful estimate, no longer in serious doubt. The JWST observations have, by every careful description, transformed our understanding of how the early universe operated. The detailed work to understand the implications continues. As you drift into sleep tonight, consider what you have learned. 12 billion years ago, at cosmic ages that should have been too young for substantial galaxy assembly, the universe was already producing organized disk structures with stellar masses of hundreds of millions of solar masses. The galaxies that the standard framework said could not exist were already there. They had already lived through complete cycles of stellar evolution. They had already enriched their surrounding gas with heavy elements produced by previous stellar generations. The cosmic clock was, in this picture, running faster than we previously believed. The implications for everything we thought we knew about the early universe are, by every careful description, substantial. The work to understand these implications will, by every careful estimate, continue for many years. The next several decades will be, by every careful description, a particularly important period for the development of our cosmological understanding. The framework we currently rely on is, by every honest description, gradually being replaced by something more sophisticated. The transition is, by every careful estimate, only beginning. Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.